Alright, hello guys, welcome back to another video. So in today's video we'll be discussing problem 2894, which is divisible and non-divisible sums difference. So in this problem we're given two integers and an m, and they're both positive, um, so keep that in mind, and there are two integers that we have to make. With num1, which is the sum of all integers in the range 1 through n that are not divisible by m, and num2, which is the sum of all integers that are divisible by m in the range. So basically we just have to return the difference between sum1 and sum2. So that's basically what the problem is. Now let's go into how we are able to do it, like what's the strategy behind doing something like this. So let's start off by examining the brute force approach for this problem. So this problem, I think you've already might have thought of this, but this problem can be easily solved using the brute force approach. Now, this approach involves basically setting up a counter, like two counters. One counter is for the sum that is divisible by m, and the other one is the sum that's not divisible by m. And basically all you're essentially doing is the looping through the numbers 1 through n, and then if it is divisible by m, in other words, if I mod m is equal to 0, then you accumulate for sum 1, and then otherwise you accumulate sum 2. And essentially what you're doing is just returning sum 2 minus sum 1. So pretty straightforward there. So let's look at the time complexity now. So time complexity for this is O of n, and the space complexity is O of 1. It's O of n because we have to loop from 1 to n in order to accumulate all of the sums. And because of that, the number of operations that we have to do increases proportionally with n, which means that if n gets bigger, that means that the amount of operations that we have to do will also get bigger with n. So space complexity is big O of 1 because we don't have to allocate any additional space for another data structure like an array or something like that. So, space complexity will just be constant there because we're only creating like two variables. So that's why. So the question now is, can we do better? And usually speaking, big O of n time complexity is good to have for a problem. However, notice that we aren't given an array in this problem. Instead, we're given only two integers. So we have to think about whether or not this is actually the optimal time complexity for the problem, and if we can do better than big O of n. And it turns out we can actually do better than big O of n. And we can do that by using a bit of math, as I'll explain now. So, optimized approach is as follows. So, recall, if you haven't learned this formula, it's okay, but recall that the sum from I to n of I is equal to n times n plus 1 over 2. So, this is like a standard sum formula. So let's explain, in case you haven't seen this formula, let's briefly explain why this formula works. So assume that we have a list of numbers from 1 to 5 in a specific order, listed from least to greatest as shown here. So let's try and add up all the numbers starting from the beginning and ending at the end, obviously, with the 2 pointers from 1 to start and 1 to end. And basically what we're going to do is keep going inward with the 2 pointers until they meet in the middle. So let's start by adding up 5 and 1. So as you can see, 5 plus 1 is 6. And so you move both pointers inward now. And 2 plus 4 is also 6. And eventually you meet in the middle, and the remaining sum is just 3. So notice that as we are taking sums from two pairs of numbers, right, the sum will remain the same. In this case, the sum will be 5 plus 1, which is 6. So the sum is 6, And in total, we get two pairs of numbers that we have to add up. So that's 5 minus 1 over 2. Um, so now we have the sum for those two, which is 5 plus 1 times 5 minus 1 over 2. And we also have to add up the number in the middle as well. So that number will be 5 plus 1 over 2. In this case, it's 3. And so 5 plus 1 over 2 is the correct amount that we need. And as you can see, this adds up to 15, which is precisely the sum from 1 to 5. So for any odd integer n, we can actually generalize this form to be in terms of n. So let's do that right now. Okay, so now we have the formula in terms of n. So now let's just do some simplification and we'll get the answer here. So notice that the answer that we got is precisely n times n plus 1 over 2, which is exactly what we needed. So let's look at the even case now. So for even numbers, this derivation actually becomes much simpler because if imagine you're having like a even number for n, right? Let's say n equals 6, for example, right? So if we have n equals 6, there are going to be precisely three pairs of numbers that we have to add. And as we've seen before, each pair of number will be n plus 1, have a sum of n plus 1. So just multiplying these two together will give us our answer. So, since we've proved it for even and odd numbers, it will work for any arbitrary integer n. So let's go back to the problem real quick and try to see how we can apply this concept to solving our problem here. So let's suppose that we have the range 1 through 10 as the input. So in other words, n is 10 and m equals 3. So basically we're taking all of the numbers divisible by 3 in this range and then adding them. So notice that there are 3 elements that we have to add up, so like 3 target numbers. And also notice that 10 divided by 3, and if you take the floor of that, you get 3, which is precisely the amount of elements that we have in the list that we need to add up. So also notice that you can factor out 3. In this case, since it's divisible by 3, we can just factor out the 3 from each of the terms that we have to add up. So we get 3 times 1 plus 2 plus 3. And this can be written as summation notation as 3 times the sum from I equals 1 to 3 of I. So we have the sum. So naturally, we can generalize this concept to any integers n and m. So how do we do that? So we have determined already that there are three numbers from 1 to 10. In this case, there's going to be floor of n over m integers from 1 through n, as you can see here, that are divisible by m. So we'll write m, 2m, 3m, etc. until m times n over m. So yeah, we can do the same thing before. We can factor out the m, and then we get some integers 1 through floor of n over m. And we can write this as a sum as well. So m times what I equals 1 to the floor of m over n of I. So that's our final sum. And recall that the answer that we have to get is sum of the elements that are not divisible by m minus the sum of elements that are divisible by m. So how do we get the total sum of elements that are not divisible by m? Well, this is actually simple. So we can just have the entire sum of the list of numbers from 1 to 10 or 1 through n, which will be I equals 1 to n of I. And then we can subtract it by the number of elements that we know are divisible by m, which we already calculated. So we have that. So now let's try to plug everything in to find the final answer. So we have the sum of elements that are not divisible by m minus the sum of elements that are divisible by m. So let's substitute everything in and simplify and see what we get. Okay, so as you can see, we got a closed form solution that involves m and n. So basically, all we have to do in the code is simply type in this expression here, and then that's it. So basically, we just say, like, it can be like one line. We can just say like return n times n plus 1 over 2 minus m times floor of n over m, floor of n over m plus 1. So usually in programming languages, floor of n over m can just be written as just like that, like with the division sign. In the case for Python, however, make sure to use double um, division sign for floor division. Other than that, that's all you have to do for that. So that's our final answer. And let's try to analyze the algorithm now, see how much time space complexity it has. So time complexity is big O of 1. So the reason why it's big O of 1 is because no matter how large n is, we'll always be doing a constant operation. So in this case, we just have to plug in n and m in the formula that we have above and just get the answer. So basically the operations aren't really increasing as n is increasing. So that's why it's big O of 1. And space complexity wise, we didn't create any additional data structures or anything. So that's why the space complexity is also a big O of 1. So yeah, that's it for the problem. Hope you enjoyed this. Thanks for watching. Goodbye.